Welcome back. Now, we are trying to compute the Mordell-Weil group of an elliptic curve. And what we're going to do first is a method that is called the complete to descent method. And the complete to descent method is I think that's an awesome achievement of ingenuity in that we've studied all these sort of like pairings and injections that have come up along the way. We have the Weil pairing, the Kummer pairing, and a map that comes from Hilbert's Theorem 90. And we're going to put all these tools together to compute the Mordell-Weil group in one way that is, so we're going to go from like the very abstract, like these definitions and maps, to something really concrete to be able to compute the Mordell-Weil group. So by the way, so remember, so we have the Weil pairing that gives us a map between a pair between M torsion and M torsion, and it gives us a root of unity. We have the Kummer pairing between an elliptic curve and the Galois, absolute Galois group of Q, of K, that goes to M torsion. We computed the left kernel of the Kummer pairing, and that then induces, if you mod out by the kernel on the left, induces this map delta E that, because we've mod out by the kernel, is an injection into the Homs of Galois of the Galois group of EM into EM. Now that is great, and that we exploited that already to prove the weak Mordell-Weil theorem. We proved that these Homs actually, the image lands in somewhere something smaller than that, and we were able to compute a bound for the image, for the size of the image, and that gives us the weak Mordell-Weil theorem. That, however, that's as much mileage as you can sort of get out of that, and we cannot. There's the hard part is to make that computational, so we can actually, in practice, try to compute what those are. Basically, the best you can do is come up with a bound depending on the class group of some extension of K and so on. So that is only so useful. Great. But now comes cohomology. This map, by the way, if you've seen the videos on cohomology, the introduction on group cohomology, this map is a connecting homomorphism between an H0 and an H1. And similarly, Hilbert's Theorem 90, which tells you something about a cohomology group vanishing, induces a map between K, the units modulo M in K, and the Homs of Galois into mth roots of unity. Now that is actually an isomorphism. That's part of the corollary of Hilbert's Theorem 90, and we're going to exploit that. In which way? Well, take delta first. Delta is going to take E mod M and give us a Hom. Okay, so these Homs land on M torsion. So what about if we put this where whatever P lands on an M torsion given a Galois element, that element, and we're going to throw it in here into the Weil pairing with a fixed pair T, and that is going to give us an mth root of unity. What that gives us in all is a map from fixing a point P. They are maps from Galois to mth roots of unity, and that is exactly what these are, maps, Homs from Galois to mth roots of unity. And by Hilbert's Theorem 90, we know exactly that all of them look like this. So what we've done is the following. Take the Weil pairing and evaluate it at the image of the Kummer map. Okay, so remember, so this is nothing else than the Kummer map evaluated at P, and then leave the sigma, leave the Galois element as the variable. When I evaluate at that and a fixed T, what I get is a Hom. It's a Hom from the absolute Galois group to mth roots of unity. By Hilbert's 90, that is of this form, is one of those delta K B for some B. For some B that will depend, this only depends on, well, on E, but it depends on P and T. So it gives you a B that you put in there, and it gives you the hom that this Weil pairing gives you. So all in all, we get this, and we're going to exploit that in as follows. So here is what we're after. One, there is a bilinear pairing. So if you didn't have enough pairings, here's another one. There is a bilinear pairing B that goes from EK mod M, that's the P, cross M torsion, that's the T, to where? To classes modulo mth powers, such that B of PT is the unique class modulo mth powers, such that EM of delta E of P evaluated at sigma cross T is delta K of BPT evaluated at sigma for all sigma in the absolute Galois group of K. Okay, so that gives us a bilinear pairing. Now we have experience with bilinear pairings. What I actually want to get my hands on is this. So let's compute the left kernel, because that's going to give me an injection into some homs. And hopefully these homs are more computable than the other homs we had. So let's compute the left kernel. The pairing is already non-degenerate on the left. Perfect. There's no kernel. Therefore, we get an injection of E mod M injects into the homs that grow from EM to K cross modulo K cross to the M. The Kummer pairing gave us a hom like this, an injection like this, but notice that the other one, the image of the homs was the absolute Galois group of Q, which is a monster, not the monster group, it's a monstrous group. It's something gigantic. But now, look how awesome this is. This is giving us maps from EM, which is a very easy to understand abelian group, finite abelian group, into something that is also easy to understand, K modulo mth powers. Okay, this is fantastic. Okay, so P maps to BPT. Oh, no, sorry. It maps to the BP star. Okay, so now the variable is whatever T you put for an M torsion point. Great. Now, what else is in your shopping list for an injection like that? It should be that, well, I would love to have homs that go from something finite, yes, into something finite. No, that is an infinite abelian group. It's easy to understand, but that is an infinite abelian group. So let's cut it out. Let's cut out this to be finite. So we inject this into something that is finite. Okay, so that is the last part. And we know how to do this because we've proved the weak Mordell-Weil theorem. So it turns out that if you let S be, guess what, places, infinite places, union the bad primes of EK, so the bad places, the bad finite places, union primes, prime ideals that divide M, okay, take S to be that set of places, then the image of the pairing of Homs in the pairing B lies in what we're going to call KSM. KSM. So let me start from there. Okay, so let's start over with part C. So we were hoping to find an embedding of E mod M into something that is finite. The image of these, the domain of these Homs is finite. It's a great finite abelian group. We know all about it. This is infinite. So we want to find something that is finite in here, that we're hoping that the image lands on something that is finite, and it does. It does because we saw something like this in the proof of the weak Mordell-Weil theorem. So let S be a set of finite places. So it's going to be a set of places, the infinite places, and then the places that are bad reduction for E over K, and places that divide M. Okay. Then the image of the Homs in the pairing, the image of these Homs of the pairing B lies in KSM. KSM is also something, also some gadget that we saw, are classes of units of K modulo mth power, such that the order of vanishing at places not in S is 0 modulo M. Okay, so hopefully you remember that also showing up in the proof of the weak Mordell-Weil theorem, and in fact we proved that KSM is finite. When proving the weak Mordell-Weil. Okay, so what that means is that the image is going to land on homomorphisms from EM into KSM modulo squares. Okay, and finally, even better, the pairing may be computed as follows. So we can tell what the image is for every point as follows. So if you have a point T of M torsion, we choose Ft and Gt as in the definition of the Weil pairing. Okay, remember with the divisor of Ft being Mt minus Mo, and such that Ft composed with multiplication by M is Gt to the mth power. Then if P is not T, BPT, it turns out to be congruent to Ft of P modulo mth powers. So I can find rational functions with that divisor. So I can find the function f of the Weil pairing, and this is telling me that the image of a point P cross T via B is actually congruent to FTP modulo mth power. So I can actually compute the values of this pairing. So this is very, very good. And so let me show you even farther how great this is. So so how is this? How does it help? Particularly the computation part. Well, it says the theorem, which we are going to prove in a second, says that this is congruent to Ft of P modulo K cross to the mth powers, and that BPT is in KSM. right? So KSM I can compute. I know my places, so I can compute classes of elements of K that are representatives in KSM. So what I'm going to do is look at possible images in KSM cross KSM and see if they come from something. Okay, so because I don't know the Mordell-Weil group, so if I know the Mordell-Weil group, if I know a point, I can throw it into KSM. To compute the Mordell-Weil group, I need the opposite. I need the other way, that if I have a pair of possible values of B in KSM, I need them back, okay, into something. By the way, the M torsion, remember that the M torsion is bicyclic, right? The M torsion is Z mod M cross Z mod M. So there's two generators, T1 and T2. So you actually only need to know where T1 goes and where T2 goes to know all the possible values of BPT. Okay, so I need BPT1 and BPT2, where T1 and T2 are generators of the M torsion. So there's really pairs that I need to compute, but in any case, so now for each, for each pair, B1, B2 in KSM cross KSM, I'm going to try to figure out if there is something on the elliptic curve that maps there. If so, then there is a point in that lands on my elliptic curve such that B1 is congruent to FT1P. So I'm going to put EM, as I said, generated by T1 and T2. Okay. Then B1 has to be congruent to FT1 of P modulo mth powers. So there is some other element of K. So modulo some nth power in K. And then the second element has to be congruent to ft2 of p modulo nth powers. Okay, so really what this gives me is a system that I'm going to call C, which is I need x and y such that y squared equals x cubed plus ax plus b, that it lands on the elliptic curve, and then that I have b1 of z1 m equals ft1 of xy, and b2 z2 mth powers ft2 of xy. Okay, with x, y, z1, and z2 are going to be in k, k, k cross, k cross. So I need to find a solution to that system. Okay, this is what we call a homogeneous space. That terminology will become a little clearer later when we actually work in homogeneous coordinates. And what we're going to do is try to simplify this even farther later. Okay, but for the time being, I'm just going to leave it here, that this gives us a computational way to actually try to solve some systems. There's only finitely many possibilities for B1 and B2. So once you go through all the possibilities for B1 and B2, there's a finite set of these to check. Okay, these ones depend on B1, B2, and those homogeneous spaces give you a finite family of spaces to check for solutions. Very good. So now, right. So what we're going to do now is prove the theorem, and then we'll get back to this.
Professor, just a
really
minor question.
Yeah.
So when we say that we're calling this system C, again, very minor, are you using C as like an indexing, just like should that denote like the space C, or
Yeah,
Oh,
It's
sorry.
a name for the space. It's in fact a curve. It doesn't look quite like a curve, but
Mhm.
it turns out it's going to be some curve um, that we are trying to find points on. These curves are actually going to be um, over k bar. They're going to be isomorphic to the elliptic curve itself.
Mhm.
So in any case, these are. I'm just going to let it C for just to give a name to the system. Um, of equations for now, and so it's just a label for it.
Okay, cool. Sorry, I had thought that
Yeah,
it was like enumerative, but I get what we're doing now. Thank you.
yeah. All right. So now let's prove the theorem. The first part was that there is a pairing, right? We have the first part of the theorem is that there is a bilinear pairing B from here cross EM to classes modulo nth powers. And the existence of it actually, the fact that this is that exists and is well defined follows. So existence as well defined follows from, as we explained, from Theorem 90, Hilbert Theorem 90. So from the fact that k cross modulo k cross nth powers is isomorphic to homomorphisms from the absolute Galois group of Q to mth roots of unity. Okay. And the fact that that the Kummer pairing is the fact that K and EM, that the Kummer pairing and the Weil pairing are bilinear, imply that B is bilinear. I'm not going to do that, but you can easily check that that happens. Okay. Now for part B, we want to prove that the kernel on the left is trivial, that is already non-degenerate on the left. So let's suppose that it is not, that there is something in the left kernel. So suppose that BPT is 1, the class of 1 modulo nth powers for all t in EM for some p. Okay, we're hoping that this p is just 0, or that it's 0 in the quotient of E mod m, so a multiple of m. What that means, if you unpack the definition of BPT, is that for all t an m torsion, and for all sigma a Galois element in the absolute Galois group of Q, EM of kappa p sigma comma t is 1, is the trivial root of unity. But if this happens, EM is non-degenerate. Remember, EM is non-degenerate, and therefore kappa of p sigma would be trivial for all sigma. But so this element would have to be trivial if it was trivial for every t, because EM is non-degenerate. However, the Kummer pairing, we know what the left kernel of the Kummer pairing is. The left kernel of the Kummer pairing, left kernel of kappa, we know that that is the mth powers of the rational points. Okay, and therefore p would be 0 in E mod m, and therefore it is non-degenerate on the left. Okay. Now for part C, we want to prove that the image of these Homs, or that BPT, lands in where that lies in KSM. Okay, so remember, so KSM here is again classes, B's, such that the order of vanishing of B is 0 modulo M for all things not in S, where S is infinite places, bad places, and places dividing M. Okay. So how do we prove that? Well, we want that the image is in KSM. All right. So let just take a B, which is a BPT, and let beta be an mth root of BPT. Then we know that actually K adjoint beta is contained in L, which is equal, remember our L, mth roots of points defined over K. Okay, why is this? Why is this? Well, suppose that if sigma is in the Galois group of K bar over L, so if sigma fixes L, then forcefully kappa of P sigma, which is, remember, Q sigma minus Q, where Q is an mth root of P, Q would be in L, sigma fixes L, so sigma fixes Q, and this is O. Okay, so that implies that EM delta EP sigma of T, delta EP sigma is kappa P sigma, that's EM of OT is 1, but on the other hand, this is delta of BPT applied to sigma. So what this says is that BPT needs to be 1 if it is going to be the trivial thing, and that means that, but BPT or this map is defined by sigma of beta over beta every time, and that implies that that sigma of beta is beta for all sigma in the Galois group that fixes L, and therefore beta is an element of L. Okay, so those betas, if you take a BPT and do an mth root of that, the betas that you get are part of this subfield L. But we proved, so we just proved that if beta is an mth root of one of those, then K adjoint beta is contained in L, which is K adjoint mth roots of EM, mth roots of EK, and we proved that L over K is unramified outside S, and therefore if nu is a finite place that does not divide M, then we saw also that this is unramified if and only if the order of vanishing at nu of B is 0 modulo M, and therefore BPT is in K as M. Okay? Now, one part remains of the theorem, which is the computation. Okay, the fact that we can compute the pairing. So we want to prove that that BPT is congruent to ft of p modulo mth powers. Okay, so let's see if I have enough room. Let Q be in E and P such that M times Q is P, and beta be an element such that BPT is beta to the mth power. Okay. Then for all automorphisms of the Galois group, we have that EM of delta EP evaluated as sigma comma T is delta K of BPT evaluated at sigma by definition of BPT. Okay. And this, remember that the Kummer map is defined by Q sigma minus Q. So this is EM of Q sigma minus Q comma T is, and if I have one mth root of B, that's beta, this map that I get through delta K is precisely sigma of beta over beta. Okay, so I have a way to compute the Weil pairing. That's what this is telling me. But I know how to compute the Weil pairing. The Weil pairing, remember, it was the function gt evaluated at a point x, any point x, plus q sigma minus q over gt of x. And this is telling me that this is also sigma of beta over beta. Okay. If, as I said, this works for any x. So put x equals q in the definition of the Weil pairing, and what do you get? You get the gt of q with sigma acting on it over gt of q is beta with sigma acting on it over beta. So this is giving me two ways of computing this this Hom. I can either let sigmas act on beta, or I can sigmas act on GTQ. But by Hilbert's 90, those Homs, that's an isomorphism. So beta and GTQ have to be in the same congruence class modulo mth powers. Okay, so the fact that delta K is an iso tells you that GTQ and beta are in the same class modulo mth powers. So I can raise to the mth power, and this still will be true. And but you see, GT cubed to the mth power, that's f of t composed with mth, with the multiplication by m map, by the definition of the f and the g. Okay, so recall that by definition, ft was gt to the mth power. Okay, so what I get out of this is that ftp is ft of MQ, but that is FT composed with M, that is GT of Q to the mth power. But I just computed that GTQ to the mth power has to be congruent to beta to the mth power. And beta to the mth power is no other than BPTQ, that BPT, modulo mth powers. And that is what I wanted to prove, because what I proved is that FTP is congruent to BPT modulo mth powers. Okay, so that gives me a computational way to compute the pairing B. Right, let me stop here, and then we're going to do a concrete example. We're going to go one more layer of concreteness and actually do a complete descent for m equals to 2 with all of this in mind.